functions defined by integrals, and the second part of the fundamental theorem of calculus. So consider g of x. G of x is the integral from a to x of f of t dt. And so what we have is we have this function f of x, and there's the position a, and then what we're doing is the x is the second boundary, and of course as we get different values of that x, we'll get different areas under the function, and g is defined as a function of that x. So as we move x, we get a new area and a new value of g. And so this is one way to define a function. It's a function defined in terms of an integral. And one example of this would be the Fresnel function. The formula is written here, and this is a function that is used, historically it was used in optics, and in modern times it actually is used in the design of highways. So believe it or not, it's an incredibly useful function, a function defined as an integral. Now the question is, what happens when we take the derivative of such a function? What happens when we take the derivative of the integral from a to x of f of t dt? Well, not surprisingly, g of x is an antiderivative of f of x, so if we take the derivative of an antiderivative, we get back to where we started from. And so what this will be is just the integrand f of x. And this statement right here is part 2 of the fundamental theorem of calculus. It's not really a separate part. Really what it is just another statement of the core idea in the fundamental theorem of calculus, namely that the integral operator is the inverse of the derivative operator.